I now call to order the Society's 2,385th meeting in the 146th year since its founding in 1871. Good evening, everyone.
Hi, Larry.
My name is Larry Milstein. I am the president of PSW, the oldest scientific society of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to tonight's lecture by David Smith in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., including our members and friends around the world who are watching the live stream of tonight's meeting on PSW Science's YouTube channel. We will begin with a few announcements, including a note on the PSW logo, and then turn to a reading of the minutes of the 2,384th meeting and the lecture by Nima Arkani Hamid, provided our recording secretary arrives in time to read the minutes. Ah, he's here. Very good. Okay. This will be followed by a brief recounting of the 38th meeting of the Society on Saturday, January 4th, 1873. We will then turn to this evening's lecture, followed by a question and answer period. Thereafter, I will present a small thank you gift to our speaker, make a few closing announcements, and then adjourn the meeting to the social hour. So first, a few words on the new PSW logo, which is this thing here. So I hope you all like it, because we had a contest. We looked at over 100 candidate logos, and we came up with this one, and I can tell you a little bit about it, because it has a lot of references in it. So first of all, we started out with a suggestion by corresponding Secretary Robin Taylor that we should incorporate the symbol for induction in our logo, because our founder was Joseph Henry, and Joseph Henry was the man who first characterized induction, electrical induction, scientifically. He was a very prominent American scientist, served as the first president of PSW for 7 years, till his untimely death. And so this is the sort of artistic rendering of the symbol for induction, the unit of which is named for Henry. It's the Henry. Another reference in our logo is the Earth, the pale blue dot, as Carl Sagan referred to it. And it's because we're about our planet and learning more about our place in the universe and about physical processes that take place here and on chemical and biological processes that take place here. It's also a reference. Here are these peaks, or sort of artistic rendering of peaks, because we were also founded by John Wesley Powell, who was a noted explorer, the first person to scientifically characterize the Grand Canyon. And we've had many well-known explorers as members of PSW, and part of PSW is exploring the physical world and also the intellectual world. And finally, these pieces are references of putting pieces together, which is what science does, in order, as in plate tectonics, to come up with a dynamical understanding of how the world comes to be the way it is, what it will be in the future, and what it's been in the past. And finally, in the same helical structure, we have a reference to a Feynman diagram and the exchange of energy in subatomic physics. So there's a lot more stuff in there. You know, if you have an imagination like I do. I really like this logo. I hope you like it as much as I do. And I'd like to thank the members of the PSW General Committee who were involved in getting this logo done. In particular, Jared McQueen, who initiated the design contest, and especially Robin Taylor, who made many suggestions, and a tireless advocate, or James Hewen, for this particular logo. So how about a round of applause for them? So I'd also like to thank thank our sponsors, the Policy Studies Organization in cooperation with the American Public University, and a generous donor who wishes to remain anonymous. So I am pleased to announce that the following new members have been elected to the Society. Alan Hodge, a security engineer with DataPoint Securities, interested particularly in bioinformatics, who comes to PSW through his friends Ann and Jared McQueen. Ann is PSW member at large elect and currently PSW Director of Social Media. Jared, as I just mentioned, helped with designing the logo and is redesigning the PSW website and porting all of the current content from the old website to the new website. And also tonight's speaker, David Smith, whose interests will be apparent from tonight's lecture in part. Please join me in welcoming them to the Society. I have for them a signed copy of the first volume of the PSW Bulletin. And obviously, David's here. If Aaron is in the audience, come up and I will be happy to give him his copy. I'll give yours after your lecture. And if any other recently elected members who did not receive their copy are here tonight, please see me, and hopefully I'll have a copy for you. So with that, Recording Secretary James Heelan will now read the minutes of the previous meeting's lecture on the Doom of SpaceTime by Nima Arkani Hamed.
Hi, good evening. On December 1st, 2017, at the Cosmos Club in Washington, D.C., President Larry Milstein called the 2,384th meeting of the Society to order at 8:02 p.m. President Milstein announced the order of business, announced the evening's lecture would be live-streamed on the internet, and welcomed new members. The minutes of the previous meeting were read and approved. President Milstein then introduced the speaker for the evening, Nima Arkani Hamed, professor at Princeton University and Cornell University. His lecture was titled, The Doom of SpaceTime. We have studied fundamental physics for 2,000 years and understand the field very well. So, Arkani Hamed said, it is particularly jarring when something that seemed like an essential element of how we think about how the universe turns. I apologize, I've had a day. So, Arkani Hamed said, it is particularly jarring when something that seemed like an essential element of how we think about the universe turns out to be wrong. He said that is where we are at today. 20th century scientists revolutionized physics with theories of quantum mechanics and space-time, which together form quantum field theory. Those concepts led to predictions accurate up to 12 decimal places when tested. That accuracy is what makes doubts about these theories so disturbing. Arkani Hamed described the two storm clouds he sees for space-time and quantum mechanics. The first storm cloud suggests that space-time is doomed. The second, that quantum mechanics is limited. To explain the first cloud, Arkani Hamed presented a thought experiment. To see what exactly is going on at arbitrarily small distances, we must use high energies. In a world without gravity, there is, in principle, no limit to scaling the size of a detector to see what is going on at increasingly small distances. But we live with gravity, and when there is too much mass, we get a black hole that traps light, meaning that if we build too big a detector, we will create a black hole that will prevent us from seeing what happens at the smallest distances. Thus, gravity limits our ability to measure space-time, which means our current understanding of space-time is merely approximate and not fully accurate. Similarly, the second cloud is explained by the problem of measuring quantum mechanics. To measure such quantum observables, our precision improves by how many measurements we take. But to take the infinitely many measurements required to reach almost exact precision would require an infinitely large measuring apparatus, which again is limited by gravity. This limitation means quantum mechanics is also an approximation. Thus, space-time and quantum mechanics cannot be fully accurate as we currently understand them. To be fully accurate, we must rethink our most basic understandings of physics, as there are no measurements of any sort in the interior of space and time that can belong as precise properties of the world. Arkani Hamed believes both space-time and quantum mechanics will emerge together from new principles about the fundamentals of physics. To find these new principles, we must consider how to approach the problem. As examples, Arkani Hamed described how 20th century physicists rethought determinism and how Richard Feynman's intimidating method of doing physics reduced to simple formulas. As scientists did in those instances, we must rethink the fundamentals of physics to find the simple truths. In current research, Arkani Hamed says, physics and mathematics are working on the same questions with radically different approaches. He's optimistic that those diverse approaches will bring about radical redevelopment and maybe in 20 to 50 years bring about a new grand unified theory. President Milstein then invited questions from the audience. One member asked whether geometry might be the primitive concept to build on. Arkani Hamed said we are too early in our approach to rethinking physics to believe that what we already know is the real thing. He cautioned that we must sever as much of the familiar language and concepts as possible from any new theory, stressing that we must push forward into completely new territory. A guest asked what rules the speaker relied on to present proposed new principles. Arkani Hamed responded, there are no rules yet. But we have enough data to know that certain results are certain. We can thus use that data to test the viability of new language and new theories. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 10:08 p.m., President Milstein adjourned the 2,384th meeting of the Society to the social hour. Temperature, 7.8 C. Weather, clear. Attendance, 159. Respectfully submitted, James Heelan.
Thank you, James. Thank you, James. Are there any comments or corrections to the minutes? Carl.
I thought that his primary appointment was as a professor at the Institute for Advanced Thinking.
Nope. The Institute for Advanced Study.
Okay, yes, not Princeton.
I don't know if they do any thinking up there, but they do a lot of studying. Yes, it is. His principal appointment is a professor at the Institute for Advanced Study. Okay. Are there any other comments or corrections? Hearing none, I will entertain a motion from a member to approve the minutes. Eric, do I have a second? New member, second. All members in favor? All members opposed? The minutes are accepted unanimously with one correction and will be posted with that correction to the website in due course. The 38th meeting of the Society was held on Saturday, January 4th, 1873. The bulletin does not report the time of day of the meeting, and it does not report the location of the meeting. There was no Cosmos Club then, so it was not in the Cosmos Club. President Henry presided over the meeting. As many of you know, President Joseph Henry was a primary founder of PSW and its longest-serving president, leading the organization from 1871 until his death in 1878. He was the preeminent American physicist of his time, known internationally for his pioneering work on electricity and magnetism, particularly his work on electromagnetic induction, work that led to the invention of the telegraph and the telephone. Among other important roles, Henry served as founding and first secretary of the Smithsonian Institution. At this meeting, Professor J.R. Eastman presented a report on his study of the thermometers then being used at the U.S. Naval Observatory to correct for atmospheric refraction. Several thermometers were placed in various locations in and around the observing area, and 60 measurements were made with these thermometers from May 8th to July 16th, 1870. The measurements were compared to measurements made with a standard thermometer over the same period. Professor Eastman is not reported in the bulletin to have explained what the standard thermometer was, but considerable differences were observed, and Dr. Eastman reported that these limited the accuracy with which the refractive correction could be calculated. The building depicted on the left is a sketch of the Naval Observatory as it appeared then. The building on the right is Naval Observatory as it exists now, not far from here, actually. I was unfortunately not able to find images of the thermometers that were in use at that time in the observatory. The thermometer on the slide is merely a stand-in. John R. Eastman was among the most prominent men of science of the time. He was one of 12 professors of mathematics in the U.S. Navy. He served as president of PSW and of the Cosmos Club. And he was the first president of the Washington Academy of Sciences in 1898. He also served as vice president of the AAAS. He had been described as a tariff for revenue, gold standard, honest money Democrat. Mr. T. Annabelle reported on the meteorology of Japan. He, of course, did not have the benefit of Earth imaging satellites, which provided the image on this slide. The bullet does not report what Mr. Annabelle reported. At the 7th meeting on May 27, 1871, the same Mr. Annabelle had displayed a vial of dust with organic matter from Bitlitz, Armenia. The significance of the vial, the dust, and the organic matter remain a PSW historical mystery. Annabelle was a founding member of PSW, but I don't know much more about him. Maybe there are a lot of bacteriophage in the dust. We now turn from the 38th meeting in 1873 to the 2,385th meeting taking place tonight in 2017 and to tonight's lecture. It's my pleasure to introduce tonight's speaker, David Smith. David is the James B. Duke Distinguished Professor in the Department of Electrical and Computer Engineering at Duke University, a director of the Duke Center for Metamaterials and Integrated Plasmonics, and founding director of the Metamaterials Commercialization Center at Intellectual Ventures. David's research has focused on unique electromagnetic structures, including photonic crystals, metamaterials, and plasmonic nanostructures. He and his colleagues demonstrated the first negative refractive index material, perhaps actually the first such material that has ever existed. David and John Pendry developed a revolutionary approach to electromagnetic design called transformation optics, and with it designed a metamaterial they predicted would act as an invisibility cloak. Theory is one thing, reality another. And not content with the merely theoretical, David and colleagues fabricated the actual metamaterial they had designed and demonstrated its ability to act as an invisibility cloak. Their 2006 paper reporting these results is a landmark in materials science and was the subject of widespread publicity in the popular press. David's interests extend well beyond the laboratory, and in addition to his scientific research, he has been working to transition metamaterial concepts to commercial applications through his association with Intellectual Ventures and by serving as co-founder and/or advisor to a number of startups aiming to develop metamaterials-based products, including Evolve Technology, Echodyne Corporation, Pivotal Comware, and Chimeta Corporation. He is the author on over 300 publications in the area of metamaterials and more than 70 patent applications and patents. He has been named a citation laureate every year since 2009 by ISI Web of Knowledge for having among the highest number of highly cited papers in the field of physics. Among many other honors and awards, David was part of the 5-member team that received the EU's Descartes Research Prize in 2005. He was selected as one of the Scientific American 50 in 2006. He is a co-recipient of the American Physical Society's McGrady Prize for New Materials, and he was elected to the National Academy of Inventors in 2016. David earned his BS and PhD in physics at the University of California, San Diego, which is my doctoral alma mater, and a great location, and has some of the finest beaches anywhere for spending a sunny day thinking about clever organic synthesis while getting a tan. Please hold questions for the question and answer period at the end of the lecture, and join me in welcoming David to the podium. should come up.
Okay, I just have to unlock it.
We just need to be a little patient. I think you want to get your emails off, though.
Yeah, they're off. Okay, great. I think we're all set. Well, I thank you for the invitation to come and speak here, and I'm going to tell you a few things about the work I do. As was mentioned, I'm from Duke University. Just recently stepped down as the chair of the Department of Electrical and Computer Engineering, but my background is in physics. When I was at UCSD, I have a PhD in physics, and a lot of what I'll be talking about is really physics-based. So this is now a very long story. So I'm going to start at the beginning, where I started, which was really a fundamental physics exploration, and now it's become really a big business. So it's a long story, and an interesting one, and one that has actually borne fruit. And it's been great to have stayed with it from the days when everyone thought it was useless to today, where it's actually big business. So this is just some of the things that we're interested in now in my lab. I won't dwell on any of these things. It's just everything we do really revolves around metamaterials. And where we started with metamaterials, it really was a physics-inspired direction to go. And that, as we continued working in our group, as I continued working, started getting contacted by many people interested in actually taking this somewhere and seeing if it could be useful for devices or products or things like that. And that pulled me way more towards engineering than I ever thought I'd end up, so that we're actually now building systems in our lab that are fairly complicated. But to me, it all blends as part of the spectrum of what we do. So I did not know the audience, and I didn't know if everyone would be a physicist, so I'm trying to mix some things and not put up too many equations. Try to explain things in just a way that you can kind of get the feeling of what's going on and what the inspiration was. What I'll be talking about is electromagnetic waves. That's what our group really is focused on. Metamaterials now expands well beyond that, but what started for us in thinking about electromagnetic waves and how to manage them. So most people are familiar with the electromagnetic spectrum, which covers everything from radio waves up to X-rays and gamma waves, includes the optical spectrum, which is just really a small part of this overall spectrum. We do a lot of work down here in the microwave region, where the wavelength is a few centimeters, but everything here can be addressed by metamaterials, at least up to maybe the UV. This is the anatomy of a wave. This is what a wave looks like. So a wave is characterized by its wavelength. It's a periodic field variation. It has electric fields, and it has magnetic fields. And those electric and magnetic fields oscillate back and forth. And if you want to end up controlling a wave, you've got to somehow control both the electric and magnetic field to fully grab hold and make it do something. So it doesn't work in space. What light does or waves do is just travel in a straight line in space. That's important. They don't interact with each other. So the way to control them is to use materials. So controlling waves actually becomes a materials physics discipline. And really that's where I enter and where we enter with metamaterials. Again, not many equations, but Maxwell's equations are the equations that govern electric and magnetic fields. And if you don't know what these mean, it's fine. All you have to know is that there's only electric and magnetic fields to worry about in electromagnetism. And there's a couple of other parameters, and those parameters only become important when you have a material. These represent all the properties of the material. You have mu, which represents magnetic response, and epsilon, which represents electric response. So if you want to create a material that truly controls everything perfectly, a wave perfectly, you want to control epsilon and mu. And then from these, you derive a couple of other parameters. One that probably everyone knows. You can solve these equations, or you can combine them to get a wave equation. And naturally, in that wave equation, you get this parameter n, which is the index of refraction. And if you work that out, the index of refraction is the square root of epsilon times mu. So really, from the macroscopic point of view, if you have a material, we know that there's atoms and molecules that make that material up. But as someone who's interested in just what happens to electromagnetic waves, all you need to know about the material is what is mu and what is epsilon, and then you can go forward and figure out what that material is going to do to your wave. And using these parameters, really you get most of what you need to know about the material. So if you're going to synthesize a material for optics or to control electromagnetic radiation, these are the parameters that you care about. Oh, I circled them. Okay, animated slide. Again, if you don't know what, or can't think of electric fields and magnetic fields and what they do, or are unfamiliar with the field-matter interaction, just a quick example that I thought of is, if you think of wind blowing through a field of grass, you see the grass moving. You really don't see the wind, but the wind is composed of particles, but you can just pretend it's some pressure field or velocity field, and you can imagine the wheat or the grass as being the material or matter that interacts with that field. In the same way, you have electrons in your material, protons too, but electrons are light enough that if they experience an electric field, they move up and down in the direction of the field. If you have a magnetic field varying, you also get motion. That motion is a little different. The electrons or the charged particles will run in orbits. So you have two different types of response, and these are the kinds of response at the molecular level or at the atomic level that you want to control by your material. This is how the materials respond. So this is important as we go through this. This is the basics of response. You apply a field, and your electron moves in response to that field, just force and response. So now, what happens at a material? If you want to understand what happens at a material, you can go to a very, very primitive, simple model, which is a harmonic oscillator. You can imagine that you have some charge on a spring, because in materials, your electrons are bound to atoms, and a good model, a perfectly good model, is an atom on a spring. And if you apply a field, that electron or particle is going to be pulled in some direction. Imagine the opposite sign here, so the thing's neutral, because materials are neutral. And if we include that response and that mass, what happens is you have a force equation like this, which you can solve pretty easily to get a polarizability or a polarization, which is how much this thing moves, times the charge, that has this form here. So rather than taking you through this, if you haven't seen it before, it's useful just to animate it. And so hopefully this works. What I'm doing here is I'm beginning with a field at a very low frequency, and you can see this is a charged particle. I didn't put all the notation on it, but you can see what happens at very, very low frequencies. The particle is just going to move in the direction of the field. And the spring is a restoring force, and I'm slowly increasing the frequency here. And so as we increase the frequency, you can see that as we get towards this resonance point, this starts moving larger and larger, so you get more and more deviations. So if you want your material to respond, you want to work near the resonance, and you really see that this is beginning to pick up pretty considerably. As it gets near this resonance, you see it's pushing very, very far, and you also see that it's overshooting a bit, which is standard, because when you hit the resonance, it means for a very little bit of drive, you can get very large deviations. But once you go into here, in this region here, what you can see is something very interesting happens. The applied field now seems to be in the wrong direction compared with the motion of the charge. And if you think of charge response, if you think of putting a force on something and seeing it move the other way, you might be a bit surprised. But this actually is an important material phenomenon. It happens, and it's often called negative materials, and I'll explain that in a second. But you can see by the time you're over here, and all I did was solve that equation on the previous slide by putting a time-dependent field in, which is increasing frequency. Once you're past this resonance, the motion of the particle is opposite to the applied field. That's interesting. Why is it interesting? Well, for a lot of reasons, but hopefully you can see it there. That animated the whole thing. We have atoms, and those atoms really obey that model. Atoms and molecules actually obey that Lorentzian kind of model that I just showed you. And if you take these molecules and put them together, this epsilon is really just measuring this dipole moment, or this response, this polarization that you get from each of these constituent atoms. And likewise, mu is really, you put a collection of atoms together or something like that, and that mu is just an indication of how much magnetic polarization there is. So epsilon and mu are related to the, we'll call that the macroscopic model, is related to the microscopic model, which is these actual charge responses. So I got into this field when I was a postdoc because I was studying something called plasmon resonances, which occur in metals. So silver and gold, for example, are the well-known examples. At optical wavelengths, they have a negative epsilon. And that negative epsilon turns out to be responsible for making them incredibly bright scatterers. So this is just silver and gold under a microscope, dark field microscope, so you're not seeing the incident light. And they're the brightest scatterers for their size that we know of. And it's all because of this negative epsilon. What that negative epsilon does is it gives you surface modes and all sorts of phenomena that have become very associated with optics, and in particular nanophotonics and that sort of thing. So it turns out to be a very interesting material condition, and now I've explained where it comes from. This region of negative epsilon comes because you're working above a resonance, and you've got the charges can't keep up, so the field is going so fast that in the end the charges lag in response, and you end up with what's called this negative response. So it's known, it was very interesting in optics, but not all that known in microwaves. The idea of, I don't know why that does that. The idea that came along while I was working in this optics regime was, could we make artificial materials, could we make materials that might have this property, but make them at other wavelengths, like microwaves, where we had actually in the lab I was working with a lot of equipment and things were easy to make. So could we make artificial atoms? And this is what we've done. This is a picture of a lot of stuff which somehow seems to have a mind of its own. A lot of things that you'll see, I won't show all the different examples we have, but you see stuff that looks like this. And what you can think of is that these are the atoms for a material, but at microwave frequencies. It works because as long as these elements are much smaller than the wavelength and their spacing is much smaller than the wavelength at which you're operating, this looks like a material as far as Maxwell's equations are concerned. And so we can replace this with epsilon or mu or these parameters that I've talked about and solve Maxwell's equations. So that was a draw of actually creating metamaterials. And the idea for what to make, how to do it, actually came, now you don't want to go, okay, there you go. Came from Sir John Pendry, or at least that's where I ran into this concept in the 90s, because Sir John Pendry wrote a couple of papers, one in 1996, suggesting that a bunch of wires, if you did the right things, would behave like a medium that could be characterized as electric with a permittivity, and in fact could have a region where epsilon would be less than 0. In 1999, he did a similar trick, and he said, now I want magnetic response, so I could make something like this ring, and this ring actually will have a magnetic response and will have a region where mu is less than 0. So these two material properties actually gave us quite a bit of freedom, because we could now create materials with epsilon being just about anything. I showed you that resonance curve. Depending on where you're working, you could have large positive values, negative values, values near 0, values under 1, and same with both epsilon and mu. So that was really a lot of capability suddenly at our hands and worth really exploring. So that's where I sort of picked this up, this thread. So I wanted just to introduce the cast of characters. We've got wires, we've got split ring resonators, we've got electric resonators that look like this. And if you look at the metamaterials literature, you now see really thousands of variants, but this is sort of the basic 3 type that you might have. And the physical model for these is that you're creating a charge separation. So this is really the electric field is giving you electric response, given you by the charge. In this case, if you have a magnetic field that threads a loop like this, you get a current that runs, and the definition of current is charges like I showed you going around in a circuit. So this gives you magnetic response, and this gives you a resonant electric response. So it's as simple as that, conceptually as simple as that. And you can also replace these things with electric models. These are actually inductors, and just the last couple of words about Joseph Henry. This is, I guess, a tribute to him. All of these elements can be expressed as circuit diagrams to give you the effective properties of these elements, the effective dipole moments or polarization. So this connects, actually, electrical engineering with material physics, because you can actually do everything as if it were a circuit and come to work out what your effective epsilon and mu is once you put everything together in some sort of medium. So this is what we do. We take these elements, we pattern them in 2 or 3 dimensions, and each of these now becomes an effective material, and we can treat it just as we would a real material. So with that, just to reiterate, we can have mu, if we build these things in with a resonance, we can have mu that's positive, very large, very negative, or this region here where mu is between 0 and 1, which turns out to be interesting and important for reasons I'll explain later. Or we can have epsilon with these same properties. And we can mix and match and put things together and end up with really an endless number of types of materials. So this was the situation after Sir John Pendry published his papers. One thing that you think about is the index of refraction really tells you something about the material. And one of the simplest things you can see, this is a solution of the wave equation. Most people know this if you've done any physics. It looks like this. And the index tells you really a lot of things, but for example, tells you the wavelength and the material that you're working with. But it also tells you if the material is opaque or transparent. What you can see is if epsilon and mu are both positive, which is like most materials, then the square root of epsilon times mu, you can take it, it's real, so it's no problem. And that tells you that that your material is going to be transparent. It may be lossy, but it should be transparent. If epsilon or mu are negative, then you can see that the product is going to be negative, and the square root of a negative number is imaginary, so it tells you that your wave cannot propagate. However, if epsilon and mu are both negative, then the product is positive, and then the index, again, is real. So I've given you a couple of cases where you could decide something about the material just by scattering a wave off of it. If both epsilon and mu are positive, then your wave comes in, it should be transparent, so you should see transmission. If either epsilon is negative or mu is negative, your wave comes in and it can't propagate through the material, so it reflects. It becomes reflective. But the weird thing is if this region here, which we hadn't thought much about, but if both epsilon and mu were negative, then according to this, it should be a transparent material again. The thing is, now that we had these building blocks at our disposal, even though this sort of material had never existed before, all of a sudden we had at least the prospect that we could make it. So these types of materials were all known. It's a little bit more exotic to find materials with negative mu, but they exist. And so all of these things were interesting, and they're interesting that we could do these things at whatever wavelength we wanted. But this was something that was a question because we hadn't seen this before. So I'm going to show you a very simple experiment. This is what I did when I was at UCSD. This was an apparatus that was in my advisor's lab. I'd used it for my dissertation, and it was hanging around. And I could use it for experiments like this. So the idea was really simple. I've shown you a lot of physics now, but now the fun part comes because now we can make materials. And if we've made the materials correctly, we should be able to predict their properties and see if it all holds together, this whole story that I've told you. So one idea was, initially of interest was, are the rings magnetic? Do we really have this region of mu less than 0? So the idea was put a bunch of rings in here. This is a microwave apparatus. You inject microwaves here. I think it was around maybe between 6 and 10 gigahertz. And then you just do a transmission experiment. You see how much gets transmitted through your sample right here. If they're rings where mu is negative, then there should be reflection, and your transmission should go down. So that's a very simple experiment to see if these rings are negative. So here's an experiment. And the experiment was, let's put wires in. Wires should be negative. We knew that from John Pendry. And if you look at the power that gets transmitted, you can see this black line. Nothing gets transmitted because that's what wires do. Epsilon is negative. Rings should be negative at some region in this band. And the prediction was about here. When we did the experiment, you saw that there was transmission, and then whoosh, a gap, and then transmission again. So that held together. It looked like the rings had a negative mu. The problem was, if you just put the rings in, you didn't know if this was because of mu or epsilon. You couldn't really prove it was magnetic or electric. So the idea was, okay, we've got rings here, we've got wires. Why don't we put them together? And if this really has a region of negative mu, then putting them with the wires, which have negative epsilon, should reverse everything. So we've got transmission, gap, transmission. Now we put the wires in, and that's what happened here with this red. Now we switch the transmission to reflection or nothing getting through, low transmission, and then where mu was negative, or where we hoped it would be negative, it changes to transmission, and then back to no transmission. So that was the idea. We had proved that the rings were negative, and so I wrote this paper up and sent it to PhysRev Letters, and they rejected it right away without review, and with a form letter that said this is not important enough for physical review letters. So I went and did a literature search at that point, and just wondered if anyone had seen a material with negative epsilon and negative mu before. And I found one paper, I'll talk about it in a second, but it turned out to be a very exciting paper written by a physicist. And so I went back, rewrote the abstract of this paper, a little bit of the introduction, and then they accepted it. And this was really what is considered one of the first papers on metamaterials, certainly the experiment. And it turned out to be interesting for a lot of reasons, but I'll just say at this point that it was the first time anyone had shown an epsilon and mu less than 0 material. And whether you think that's interesting or not, it hadn't been done before, and now using these artificial materials, we could actually create something that had only been thought about. And it had been thought about by a Russian physicist named Viktor Veselago, who published this paper in 1968. It had never been cited, and just ran across it by accident because in the title he's got electrodynamics of substances with simultaneously negative values of epsilon and mu, exactly what we were looking for. And Veselago showed that he asked a couple questions. One, is it possible to have such a condition? Does physics rule it out? And he concluded, no, physics doesn't rule it out. It's fine to have. Two, is it uninteresting, or is it interesting? And his conclusion was that it was very interesting, that it reversed a lot of the things that we know about electromagnetics. And he then postulated as to why such materials didn't exist. He himself, afterwards, I found this out later, tried for about 7 years to synthesize a material using, synthesize such a material using conventional composites and techniques, and he failed. So when I read this paper, after having written that paper for PhysRev Letters, I realized this is what we had, and it made it very, very sort of a nice first example of what metamaterials could do. So one of the predictions by Viktor Veselago was that such a material, of course, would have to obey Snell's law. And if you take the square root of epsilon and mu, if epsilon and mu are both positive, then the index is a real number and it's positive. But if epsilon and mu are both negative, then you actually have to take the negative sign for the square root. And that means that if you just use Snell's law as it is, you have to take the negative sign for the index. And that means in your refraction diagram, as you have refraction going from one medium to the other, if this is vacuum and this is some material, whereas what it might have once bent in this way towards the normal on the opposite side, you actually, what this means is that your wave has got to bend onto the opposite side of the normal. So it's really a negative refraction, which is why now we call these negative refractive materials if this is a medium with index less than -1, for example, or less than 0. So the way this all works out is you'll notice that this arrow is being drawn towards the interface, and that has to be the case if you want the phases to line up. The length has got to be n times k, so that length is the same, but the parallel component of the k vector has got to be conserved. So the only way to make this happen is to draw a diagram like that. And that really is negative refraction, and that's what should happen in a negative index material. So the next experiment we did in 2001 was to make a weird material like this, make a Snell's Law experiment, and make a prism. This is how you measure, or one way of measuring index of refraction. A wave comes in, it sees, in this case, we're coming in from the material side. Then we look at refraction as it exits this face. And what we did is we closed this up. It was a little apparatus, and we had a microwave detector around the periphery. And what you find is if we put in something like Teflon, which has an index of about 1.4, Teflon, it would give you an angle that looks something like this. And these aren't to scale, actually. If we put in our negative index material, and at some frequency, I don't know what frequency this was, but what we found is exactly what Vestlager predicted, that it came out the other side of the normal. And here you can see, just as a function of angle, Teflon, which is giving us positive refraction, and then this weird material made of rings and wires gives us negative refraction. And so that really was a proof and a testament that all this was correct. Well, almost. So in just about the time we published that next paper in 2002, it actually proved pretty controversial. And you can tell by the titles of these papers, and a lot of this was carried out in the scientific literature, but also the popular science literature. It became like a big controversy. So you can see some of these titles. This one I always point out, is there an experimental verification of a negative index of refraction yet? This was after our experiment. And I had the pleasure to review this paper. And the original title was, is there an experimental verification of a negative index of refraction yet? No. That was the original title. So at least as a reviewer, I got them to take out the no. But they were very, very critical. Problem of left-handed materials, which is what they were called at the time. And then this one, which actually was interesting, it confused people a lot and caused us a lot of trouble. But I have to say, I was a postdoc at the time, and I spent years working on things and discovering how little people cared or could get interested. So as a postdoc, to see everyone arguing about the stuff we were doing was great, actually. I wasn't too worried, but even still, it was good that people were interested in this. So I wanted to show something kind of interesting. If what I've just shown you is what happens with a single wave. If you look at two waves and add them together, which might be, for example, if you had a pulse, it would consist of many frequencies, many waves summed together. So if I have a couple of waves at slightly different frequencies, which I'm showing here, the velocity of a wave, it's well known, is given by omega over k. That's sort of the speed at which the phase propagates. And you can see it here and here. I've got two things at different frequencies, which means they'll have different k given by this dispersion relation. If I add these waves together, what you can see is a beat frequency. And that beat frequency, if you sort of work through this, should not look like this. This should be delta k and delta omega. In the end, the group velocity is actually this. And that's really the rate at which these little interference patterns kind of go. So it's different from the phase velocity. It's given by delta omega over delta k. These are two important ways to think about waves: phase velocity and group velocity. And so even though if you have a negative index material, what happens is your phase moves backwards. That's okay. It doesn't matter. If you do things right, it's because the index has to be a function of frequency. If you put in that correct dispersion, is what it's called, what you see is that the group velocity, which is kind of associated with the reality or the way a pulse would propagate, is in the forward direction. So even though these are moving backwards, admittedly it's weird, nothing's really wrong. Energy still propagates in the opposite direction of the phase velocity. So everything is fine. What gets a little weird is if you were to look at that like this, these are now modulation fronts, these are these interference patterns, and if you take two plane waves and have them hit an interface, what you can see is that the modulation fronts actually look like they're going in the positive direction. So you might conclude from this that maybe a pulse would actually would not be negatively refracted at all. This became a big controversy. It's a little confusing, but the question of what was going on here and how that could happen really consumed a lot of people's attention because it seemed like maybe you couldn't send signals in the negative refraction direction. So you can resolve this by looking a little farther back. If you make a beam, what you can see is here's your modulation pattern. If you come into a negative index material, that beam actually does refract in the negative index direction, and the interference patterns actually are not in the same direction as your energy. They're in a different direction. And this is when it's a little bit of physics can be a dangerous thing, because if you always associated the interference pattern with the direction of energy, then this would fool you. In fact, everything's fine. It's just that these interference patterns, once you refract at an interface to a dispersive material, really give you something different. And it's this aspect of what happens when you have a dispersive material that made metamaterials so interesting, because it turns out that many people were confused by what happens in a dispersive material and an anisotropic material. A couple of things that come up, for example, if you, in the back of your head from physics, know that energy is 1/2 epsilon E squared plus 1/2 mu H squared, that's wrong when you have a dispersive material. It's actually this. So some of you may know that, some of you may not, but if that simple expression for energy density, which you're not going to find this in your undergrad textbooks, but if you have a dispersive material, it looks like that. And there's many, many other tricks that make metamaterials so unusual, things like this. I used to have this animated. It stopped animating. I have to do it again sometime. But if you turn off causality and don't have dispersion, you can get weird things with a pulse. So here's a pulse coming into a negative index slab. As it gets closer, you can see that all of a sudden a pulse emerges from the other side of the slab, even before the pulse gets in the slab. And as a function of time, this antipulse propagates in the slab towards the interface, where it ends up annihilating the incident pulse, and then this transmitted pulse occurs before this even enters the medium. This, again, if you put in causality and you put in dispersion, this doesn't happen, but it's an interesting way that this violates causality. So with the controversy raged until around 2003, when our friends at Boeing, under a DARPA program, actually confirmed it. They made a better sample. This looks actually much more professional, you can see. And they took these measurements, and this is theory. This is what they found. This is an index of refraction. It's negative. And that allowed us to conclude, or Sir John Pendry concluded, positively negative in 2003. So what's interesting about this is just a Snells Law experiment. This is something that you might do as an undergrad. And now most of the DoD was involved in making these same measurements. It's just that the material was so interesting and unusual that people had to sort of see it for themselves and confirm it. So in fact, in 2003, it was so exciting that we had a Metamaterials Summit that was organized by DARPA, Valerie Browning. This is Victor Vesilago, who came for this meeting. After all those years, he was very happy. This is my advisor, Sheldon Schultz. And this is Valerie Browning, who is running the program. And I believe one of the guests here tonight, here's Don Rule, who was actually at that meeting. The idea was to bring all of the controversy together, all the people that were saying everything was wrong, and all the people that were saying everything was right, and sort of hash it out. But none of the people that came were the antagonists. Everyone was pro, so it was interesting. And I like this. My advisor and we at UCSD put together a little gizmo here and ported the whole thing up to DC from San Diego. Network analyzer hiding in the back there. And this is the Boeing sample. And what we did was modulate signals so that there was some music playing. And you could take this little detector and route it around. And when it was in the negative refraction point, you'd hear the music. And as you moved it around, as you moved away, you could compare it, for example, with a Teflon slab, which would send energy out in the direction of positive refraction. So that's the background of negative index, and negative index was something that was absolutely new and had to be explored. I won't go into all the explorations and all the things that could be done with it, just to say that it was really a kind of a spectacular coming out for metamaterials to show what you could do with these novel materials. To date, no one's actually made an application using negative index, but it really drove a lot of great science and a lot of great thought. Over the next couple of years, I spent a lot of time myself working out how to develop methods to more rapidly create materials this is sort of the concept here. You've got some artificial materials or rings, whatever they are, and whatever it is you'd like to be able to do very quickly, turn that into a material or figure out how to make it. And so I spent some time doing that on this, what we call parameter retrieval approaches. So we kind of got it down to almost an engineering. It was pretty much an engineering. We could be very accurate. And so it makes sense to figure out what more you can do. And we'd only touch the surface by making homogeneous materials. In fact, there's a lot to be gained by making inhomogeneous materials. If you can really control epsilon and mu, another type of optic you can make is something called a gradient index optic. It's another way of controlling light or electromagnetic waves, but now more with the material. If you actually make a material and change its properties, rather than relying on the surface, rather than relying on Snell's law, you can actually rely on what's called Fermat's principle, or the fact that by changing the index, you actually change the trajectory of waves. So this is what was almost unnatural for metamaterials because you had so much control over everything. In fact, so much control that no one had even really explored design methods for this. So here's an example of just making some simple optics. This is a beam steering device where we graded the index from maybe 1 to 1.6. And here's a lens. This is done by mapping the fields at every point just after the optic or through. And what you can see is the wave comes in, bends like it should. If you have a linear gradient, that's what should happen. And if you have a parabolic gradient, you've created a lens, and so you get a focus. So really, this stuff works. And these start to look more like devices. They're not like what the negative index materials are. Another thing that's interesting to do is think about holography. Holography is a design approach. One way you can make a hologram is to interfere a reference wave with an object wave. This gives you some distribution that you can, for example, if you can create an index variation with the same interference fringe pattern that you would get from these two waves, then you've created an optical element. This is the basics of holography. You may or may not be familiar with it, but really what you want to get is a surface where you have this pattern made with some material. And there's a lot of ways to do it. Metamaterials are perfect for holographic optics. You can control things. Here's an example that we did. This was for infrared wavelengths. A little element like that, a little piece of gold encased in silicon dioxide. And by just changing the geometry, you can get different values of refractive index. So you can get this whole panorama or range of index, and then use it to actually make an optic. And here's an example of the optic that was made. This was done by e-beam lithography and multi-layer fabrication. So you can see here these little elements. And just putting it in, we wanted to make for obvious reasons, we wanted it to spell out Duke. You can see we got the D, the U, the K. It turns out the student wasn't really familiar with the difference between Fraunhofer and Fresnel diffraction, so we lost the E. Just a minor point, but it worked, and we've done more since. One example of that is making a dual hologram, dual polarization hologram. You can come in with one polarization, get one thing, the other polarization, get another thing, and then just showing that this works in a sample like that. So this is another example of what you can make, and this is very, very powerful. In fact, it's created an industry. I'll talk more about that at the end, but this shows how well this can actually work. So I've talked about conventional ways of designing materials, but once you think about how much flexibility you now have, you can create epsilon, you can create mu, you can control the tensor elements, you can control it in every direction, you can create gradients. All of a sudden we realized that we had absolutely no design tool that would tell us actually how to make use of all that. So it was in a conversation that with Sir John Pendry, I was basically complaining about this situation. What do we do to take advantage of this? And he said, well, why don't we go back to this idea I had some time ago. I used it as a theoretical approach where you can take a coordinate transformation to imagine how your light will bend. But because Maxwell's equations is form invariant, they are form invariant, it turns out that you can apply that coordinate transformation to the epsilon and mu degrees of freedom and immediately get a prescription for a material that will do whatever your crazy coordinate transformation told you could do. So just to make that clear, here I've written down a coordinate transformation. Here I've written our Cartesian grid, and I've highlighted one line. And you can imagine that light will travel in a straight line. So this is what light does. You can imagine being a ray of light, and it goes in one direction, goes along a grid line. Now, if you were to plot that in the alternative coordinates given by this, what you can see is you get this warping, and now your line appears to meander and do something different. It doesn't really, because we're just plotting the same thing in different coordinates. But if we take that coordinate transformation and apply it to Maxwell's equations, we can make a material that actually does this. And here's again this same statement, but now showing you just a wave, because this approach really works for waves. It's not just a refractive index thing. It's a complete total wave management. You have a wave coming in. If you plot that in the prime coordinates, it looks the same. But if you express your wave in the prime coordinates but plot in the unprimed system, then you actually see this, all the actual wave does the same thing as your individual line did. So again, this is all just trickery, but the point is if we apply these coordinate transformations to Maxwell's equations, what we get is this. In our original frame, the wave does what it did in the prime frame. So we called this transformation optics as a way of referring to what this design approach is. And the lesson is that light in one coordinate system can behave as if it's propagating in a different coordinate system. And it's a very powerful method. And so we thought, well, what's a good example? What could we make with this that would be interesting? And so John said, why don't we think about how to make an invisibility cloak? So here's a situation. We have empty space. It's invisible. That's easy. If you just have some material with epsilon 1 and mu 1, then light goes right through it. But that's not very useful. So if we really want to control light, we have to make sure that it doesn't distort. So as it gets transmitted, it really can't be distorted. And it can't reflect either. If it reflects, then we'll see a shadow. Or if we're on the other side, we'll see some reflection or some backscattering. Whatever way we do it, we really have to get these rays outside of the region that we want to make invisible. So he imagined that we need some sort of transformation that does this. And it turns out it's really easy. You're looking at it, you want to poke a hole in space, and you want to push that hole outwards, and you want to squeeze all the lines into this ring, and you've created a cloak. And it immediately falls out. It works from every direction just because you've moved space around. That's your coordinate transformation. So it's really not a deep concept. Magicians have been doing it for a long time, and this is how you might do it. If you were looking at the bunny here, the bunny will disappear if you have light source, and you just make sure the light always avoids the bunny. And this is used to great effect by magicians. This really didn't come up when we were doing all our cloaking thing, but magicians really had the idea. The problem with this, though, is this is done with mirrors, so if you're in the wrong spot, you really will see how the trick is done, and it really requires the audience to be in a certain place and other things. It's not a true electromagnetic solution. It's just very good sometimes. So here's the mathematics. Here's the actual transformation. You can see it's very simple. It's a radial transformation, so it's radially symmetric, and you can just write it down like that. And if you take that coordinate transformation and visualize the grid lines here, we're going along this one. You can see that they detour around this region here, which we'll call the cloaked region, just perfectly, just exactly as we decided we needed to have happen. And now if you take this and apply this coordinate transformation to Maxwell's equations and to the epsilon mu, what you find is that this is your material specification. So you've got to control epsilon radial, epsilon theta, epsilon phi, and mu. So if you're not familiar with materials, this is a very, very difficult material to make. But metamaterials tell us it's possible now. And in fact, really, these two just need to be constants. You just need to create a gradient in epsilon r and mu r. Okay, so we did this work in 2006, published this idea, and I was unprepared for how much interest there would be in it. And I think it's because we coincided with Harry Potter, and it really caught on. Both John and I were surprised, and so we published this, I think I think it was in October. I forget when it was. We published it, and then there were so many reporters coming and snooping around our lab and trying to figure out where our big secret project was going that I thought we really need to do an experiment quickly. And to do that experiment, we couldn't do this. This is just it wasn't going to be a quick experiment to do that. So we thought, let's make it in 2 dimensions, and let's do a little bit of a shortcut just to show that the thing would work. And so here's what we could do in 2 dimensions with that same microwave scattering chamber. If we had a perfect cloak, this is what it would look like. And we can map these fields, and so we said, okay, if we could do this, this is what it would look like, and you can see there's no shadow, no reflection. It's perfect. It's as if this cloak plus its hidden region isn't even there. This is what the material parameters would be. Couldn't quite do that, not quickly. So we did what's called an iconal approximation, didn't worry about the impedance, but worried about the index, just to show this behavior here. And this is the epsilon mu that we need in order to be able to do it. And when we did it, or when this is a simulation, you see that there's scattering, there's some backscatter, but we were proving the fact that we're sort of routing the rays around this surface here and almost restoring it on the other side. So it's not perfect, but we thought, okay, we'll put this out there and everyone will calm down. So we did this experiment. We made this material using rings that look like this, just varying these edges here. This was done by David Schurg, who was a postdoc at the time, and varying the length of these lines here to get us a mu that would go from 0 to about 0.28 on the outer edge. And we made 10 rings. And we had to hold epsilon constant, so everything was carefully designed to get that material condition. And then we put it in our scattering chamber. This is top and bottom. You put it in there, and then you close it up. And when we did that, this is what we saw. So this was the simulation, and this is what the experiment showed. And again, there's really no material that you could, no naturally occurring material by which you could make this. It really needed to be done by an artificial material, which looks like this. And in fact, by the time you put it all together, you can see there's almost no difference between the simulation and the experiment. And only if you're very close can you see that there's like 10 bands where you're picking up the actual substructure, almost the atomic structure, we could call it, of the ring. Otherwise, it looks identical. We didn't expect it to really work as a cloak, but later on we went back and measured it. And this is the scattering cross-section, which is really what you care about. And this shows actually at the design frequency, you can see it's most of the time it's higher scattering than just the metal cylinder, but at the design frequency it shoots down and is actually lower than the metal disc inside, even though it's 3 times bigger. This was not optimized in any way, just we can do much better, but it shows that this is also a very narrow band effect, and this is inherent to cloaks. So don't go looking for Harry Potter's cloak using metamaterials just yet, because it's really not very viable. But it showed that metamaterials can do very interesting tasks, and this was sort of a grand challenge that metamaterials were able to meet. So we published this right after, about 4 months later, and expected everything to die down again. And in fact, it didn't. This really sort of hit the news and brought metamaterials to a level of hype that was probably counterproductive. I think it's great. I have these clippings now forever. Cover of the New York Times, the USA Today, really undeserving. The Today Show, Fox News. This was Dave Shurik's 3rd interview on Fox News when he thought the sunglasses would be a good idea, and lots of other shows. It's been actually a lot of fun. And then more recently, this was great for Duke. First question on Jeopardy. Duke University has developed a prototype for a cloak that grants this power just like Harry Potter's. And this was on February 27, 2015. Category was how innovative. The contestant got the answer right. The question was, what is invisibility? And the contestant won $200, which is probably the most a metamaterial cloak is worth, actually. And the story actually is fairly well detailed in this book by Philip Ball called Invisible. It's also in a lot of textbooks now, the story of metamaterials, and it's really become a science, even it's given a spotty history, and lots of other places where it's occurred. And then, of course, I always like to show this, because I think this is the mark of achievement. Twice on the Big Bang Theory, you can see Vesilago's diagram here, and you can see metamaterials there. And then in another one, I was just watching it one night, and I probably shouldn't, only I would notice this, I think, because this is our ray trace, but it was right there. So yeah, for what it's worth, it's big stuff. So now I think I've shown you the basics, and how's my time? Who's keeping my time? Yep, okay. So I wanted to go into some of the more recent work that we're doing and just show you that it's not all fun and games. It is all fun and games, but it can actually have a more profitable outcome or more useful outcome to the world. Certainly the science raised our awareness and gave us a lot of interesting things to think about, and still does. I mean, it's absolutely fascinating. But in the end, you might like to see some of it actually transition and some of the investment that was made actually go somewhere. So I want to show metamaterials is a very, very broad concept. I've talked about volumetric metamaterials, which gave us negative index materials and transformation optics and cloaks. But we can actually go into something that engineers know a little bit better, which is guided wave structures, where you have a couple of pieces of metal and you guide the waves within that metal. And the reason we might like to do that is because you sort of control the energy even better, and it's a good match to a lot of technology that exists for microwaves and RF. So these are different examples where instead of making little elements that might be like atoms in a material, we put elements on a surface, and in this case, we pattern the surface such that we have the complementary version. So instead of a split ring that looks like this, we'd have a complementary split ring, which is like an iris, where we exchange the metal and the vacuum parts. And one that's in particular interesting is a CELC, we call it, which acts like a magnetic dipole. And that's important because these things can actually radiate. And if they radiate, it means that you can make an antenna out of it. And so that's interesting. So here's an example just showing you a simulation. This is a microstrip. So you have a guided wave that's kind of bound into this microstrip. And when it hits this element, it radiates, and it radiates like a magnetic dipole, which is good. It has a polarizability that's resonant, which means that as a function of frequency, you get more radiation. And as a function of changing its geometry, you can change where that energy comes out, at what frequency it comes out. So it makes a little tunable antenna, actually. So what can you do with this? This now gives you a way to make a hologram, which I showed before, except instead of a reference wave being a plane wave, we can have the reference wave be a guided wave inside of a waveguide. And we interfere it with whatever we want out here. And now we have immediately the prescription for an antenna that will give us whatever kind of beam we want on the output. So that's a very general principle, and it's really something that can be done with metamaterials quite well. So we call these metasurfaces now, and that's our design approach. So this kind of shows what happens. You have a guided wave. It has some phase advance underneath, and this gets a little bit more for the experts, but it's exciting each of these elements, these CELCs, each of which radiates like a dipole. And then so this now forms what's called an aperture. And if you want to know what happens in the far field, you just sum up the radiation from each of those dipoles, and you get something like this. You don't have to worry about it in detail. Engineers call this an array factor, but it lets us predict what this thing's going to radiate like. So if we do that, here's just a simple example of a couple of different types of antennas one might make. And again, engineers love these. These are beam patterns, so you can see what they look like. It's on a log scale, and people very concerned about side lobe levels and lots of other characteristics. For our purposes, we've just made an antenna, and is that interesting or not? Again, for the experts, if you're familiar, the other way of doing this is something that's a huge technology called phased arrays, and they have this very similar architecture, but typically require phase shifters to achieve their function. Phase shifters are expensive, they draw power. There's a lot of other issues we don't have time to go into, but the point is that I've shown you an antenna that can potentially do beam forming or create beam patterns without all these expensive components. So the idea is maybe we could have a very, very cheap electronically scanned antenna. So how can you do this tuning? Tuning has been part of the metamaterials community for years. People have been looking for ways to do the tuning. This is an experiment that was done by my colleague Willie Padilla and others while they were at Los Alamos, where they used light to photodope gallium arsenide substrate, and they could actually change the characteristics of the transmission. So there's many ways to do it. Here's another one where I think this was integrated Schottky diodes. Again, don't worry about it, but if you don't know the details, but as a function of voltage, you could control the amount of light that would be, for example, transmitted through the surface. So there's lots of ways to bring in tuning. One way of doing it is something that emerged from around 2009, 2010, work with this company called Intellectual Ventures. And I like to mention it because while we do a lot of great stuff at the university, to take that next step to industry, you really need some partners that know what they're doing in terms of what to look for and what to think about and for manufacturing and markets and supply. So I started working with Intellectual Ventures, and they're an interesting group of people. Won't go through the details of their company, but they became very interested in metamaterials. And I want to show some of the people involved in that. Some of them you might recognize. Up here is Nathan Myhrvold, who was the CTO of Microsoft for 14 years. He's obviously being with Microsoft, he knows a lot about software, but before that, he was a postdoc with Stephen Hawking. So he's actually a physicist at heart. And he got interested in metamaterials because of the controversy. Because of all that thing I told you about, and everyone saying it was wrong, he thought there's got to be something there. So he actually came in and started working. Casey also is one of the heroes of metamaterials commercialization. And behind everything that happens out there, of course, Bill Gates is heavily involved in all of this and is, in fact, one of the big fans of metamaterials. Others who I think deserve mention because they were very much involved in the business development. This is Tom Driscoll, actually a former postdoc of mine, with Evan Frankenberg, who started a company called Echodyne. All this based on metamaterials. So I'm talking about tuning, and I talked about exotic ways of tuning, but I had a student who became a postdoc who then went to intellectual ventures and said, we need to really think about things that are going to be manufacturable and drive the cost down. So what we want to do is we want to take these little elements and we want to be able to tune them. And we want to be able to do it so that we could satisfy big markets. And so when you looked at, this is actually his chart, when you looked at the different mechanisms, what came to the top was liquid crystal. It had a lot of nice advantages, but the thing that's interesting is that you can get very, very large displays that are at a relatively low price point because of the degree of scale that exists and the degree of investment that's gone into the liquid crystal market. So people that do liquid crystals have taken care of all the row column addressing, all of the issues. And my postdoc's idea was to fuse metamaterials with LC display technology. So that's what occurred to create the first company, the first spin-off company, which was called Chimeta, which was focused on satellite communication. This is Nathan Kuntz, my student. And this really has now taken off. This was the first sample that was made. This is a metamaterial. This is just a one-dimensional microstrip. Energy goes in here. Each one of these goes off, and you can apply a voltage to change the tuning state of the liquid crystal, which changes the environment right around your metamaterial element, so that from this you can create any sort of beam pattern that you like. And it's cheap. It doesn't require a great deal of power, and is something that can be mass-produced. So this is now sort of a history here from 2012 to 2015. They're now actually rolling off the assembly lines at Sharp. This is really, really old data, so don't look at this. They're satisfying satellite communication, which has exacting standards on what your beam can look like and what your side lobe levels can be. And they've met it and are now shipping products into this space. So the companies that we spun off are Chimeta, Echodyne, which does radar, Evolve, which does security imaging, Pivotal, which does terrestrial communications, and all of these really use metamaterials as their basic technology. Just to show you, currently Chimeta is shipping to for maritime, so they're used on yachts now, and they've also are working with civilian armored vehicles. They have a contract with the State Department, for example, and they also have something going on with Jaguar implementing these. But the real proof that this can hit a large market is the combination of Chimeta with Toyota. And this is Nathan talking at the Detroit Auto Show, where they had a concept car and planned to actually bring metamaterial antennas into the Toyota fleet probably in a couple of years. So all Toyotas will be connected to satellite by this method. So I'm just going to close out with, this is a lot of the commercialization that was done at Intellectual Ventures. Just a very quick thing of where you can go with metamaterials. We got this great program, great interest from Department of Homeland Security and TSA, which wanted a new type of security scanner. So you know what you go through the airports, you know how big they are, You know that when you walk in, that you have to stop and you have to pose. And they wanted something that would actually image in real time, be very, very lightweight, kind of like this concept here, no infrastructure requirements, and of course, be really, really cheap. So we're working on that. I won't say we're entirely there yet, but there's a path. And again, this is just this type of antenna. There's some aspects of it I don't have time to go into, but taking this same metamaterial concept as a idea, this is a system that we've built. These are metamaterial panels. They've been optimized for this application. There's 24 transmit panels and 72 receive panels. This is an entirely metamaterials concept. There's no moving parts. There's no boom that scans you or anything like that. And it's not a phased array, so there's no electronic tuning. It's really just done by a frequency sweep. And so with this type of structure combined with something called computational imaging, you can actually get images, RF images of a human. And this is what you'd expect from a flat panel imaging person. At microwave frequencies, we tend to scatter like metals. So that's why this looks so metallic, actually. And you can actually take that data, and if you were to spin that person around and cleverly put everything together, you can actually get very, very high resolution images of the person. And so the idea behind this metamaterial approach to security scanning is exactly this, that someone walks through, you'll take many, many shots of them as they walk through, you'll stitch it all together and get images that look like that. So I've taken you through a lot of stuff, basic science, negative index, cloaking, things that really stimulate the imagination, to a little bit about how we're actually turning this into real technologies with real markets. So I hope that it was a coherent enough picture for you. It all started with physics, so I'm glad to be here, talking to a physics enthusiastic crowd. And we'll keep on going and see where it all leads. I'll stop there. Thank you.
So we have time for a few questions. There is a procedure for the questions. There are some brightly colored microphones with people behind them that will bring you a microphone if you raise your hand and hold it up long enough to be spotted. And then I'll call on you by the color of your microphone, and you're asked a question and not make a speech. We save those for the social hour. So we'll start with Tim up here with the red microphone.
Timothy Thomas, I'm a member, I have a red microphone. A clarification point, just to make, I didn't quite get it. I mean, there's a lot to it. These rings and wires interfere with microwaves only. They're big, right?
It depends on the size as to what wavelength you'll manage.
Do you make them small enough to deal with the visible light?
Yeah, you can make them small enough to deal with visible light, but what happens is that losses also go up. So these same structures scaled up really aren't very useful at all. There's other types of structures that are better, and you can apply the same concepts, but they just don't look the same. These work up through about terahertz, so from radio frequency to terahertz, you can use these rings and wires.
So all the ones you're doing are microwave and radio?
Yeah, well, we do optics, but I didn't talk about any of our optics.
Okay, thank you.
Questions? Surely there must be a question. James, green microphone.
Hi, good evening.
Stand up.
I have a question from Joel on the live stream. He just couldn't make it tonight due to the weather. He asks, and he is a member of the society. He asks, I noticed that you stayed with Maxwell's equations with no real introduction of quantum mechanics. Are quantum effects too small?
Yeah, this is all classical physics, and it's all we need to actually do what we want to do. There's quantum metamaterials. There's people that are looking at that, a way to manage the wave equation, which could be done with different potentials, and it's a little bit of a speculative area. I really stuck with electromagnetics because that's what we do, but acoustics is an area, Anywhere where you have a wave equation, you can manage that sort of physics. So it's a much broader topic than what I've presented, even though this is broad enough. And quantum metamaterials are certainly possible, but they don't play a role here that we really need to worry about.
Hal, with the red microphone.
No. Al Ehrlich, I'm a member. One thing I didn't get out of it, and I haven't followed this field for 10 years, is the limitation on new and really exotic applications limited by the imagination of the workers or the ability to make the materials or new structures made out of old structures made out of new materials, or where do you see as the limitations on the applications?
So when I went through that, that little animation showing where things happen, as you get near the resonance, you get this huge response and then it goes negative. That all happens around the resonance point. And where the resonance point occurs, there's a lot of losses, because I didn't show you the imaginary part, which is peaks there. So all the things that are the most exotic tend to occur right where it's lossy. So you can have these tremendously weird things like the perfect lens, which I didn't go into, but it ends up being right around that point where losses have a really deleterious impact. And so things like cloaks, things like n=0 materials, all of the things that are being talked about, your first question always is, what are the losses? Because they tend to be pretty damaging. What I showed at the end was just to show you that the same concepts, if you look elsewhere, can give you tremendously useful things, and you don't have to deal with that lossy part. In fact, you can use it to your advantage in some cases.
So you're saying it's the imagination?
Yes, I'm saying it's the imagination. That's right. Yes. Sorry, that was a long answer. Yes, the imagination.
Any other questions? We have a question over here. Stand up, tell us your name, if you're a member. It's on, don't worry. Put it up to your mouth.
The name is Raj, and the question is about one of the slides where he had showed where epsilon and mu both are 0, and how they factor n varies from positive to negative in those conditions, and in which you had actually showed a ray diagram with the negative refractive index. So the question is whether in the case of negative refractive index, when you take the negative n, is it equivalent of reflection? And if not, how is it different from reflection, that negative refraction at the interface of the two medium?
So a negative index does not make a material reflective. The negative index changes the way light enters the material and which way it goes into the material. So instead of bending light, if you have a refraction diagram, you've got a positive index material, your wave bends. If this is a normal, it bends towards the normal. If you have a negative index material, it bends toward the normal, but all the way on the other side. It's flipped, so it goes negative. So that's the meaning of the negative index.
But in the direction of the ray diagram, inside the dense material, the ray was pointing towards the interface.
Yes, yeah.
That was the question.
Yeah, that's right. So the ray points towards the interface because the phase fronts are traveling towards the interface. In fact, the phase and the group are in opposite directions. So energy is still going away. It's just the phase going backwards. And that's what I was trying to show with that interference. When you interfere a couple of waves, the group velocity goes as d omega dk, not omega over k. And this is why a lot of people call these backward waves materials, I think for various reasons, Veselago called them left-handed materials because there's a change in the relationship between some of the vectors. But that's what's happening. You caught it. Phase and group velocity are in different directions.
Thank you. I remember reading about your work when I was in high school, so it is great to actually listen to you in person. Thanks.
Further question? If there are no further questions, then let's thank our speaker, and I'll give him a nice present. So in appreciation for your taking the time to come and speak to us and giving this lecture tonight, I am presenting you with this framed copy of the announcement of your lecture tonight, signed by the members of the General Committee on behalf of all of the membership. And I also have for you a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington, signed by me, but on behalf of the membership. Thank you so much. I appreciate it. There are a few closing announcements before we adjourn the meeting to the social hour. I think the first one is, if you're not a member, please join. And it's not hard to join. As I pointed out before, you need only go to our website, which currently looks like that, but not for long. And go to the membership tab, which will bring up an application for membership form, which when you get down to the bottom, will have a little submit button that will take you to a payment page. And we will ask you to pay your dues. If we decide not to make you a member, which has never happened yet, but we will refund your money in full, forthwith. So how many of you are not members? Well, my goodness, plenty of room for growth. Please join. Well, let's see. If you are a dues paying member and you haven't paid your dues, please pay your dues. Remember, the end of the year is coming up, and if you're taking a charitable deduction, well, you might not be able to next year. PSW is a nonprofit educational organization, tax exempt under Section 501c3 of the Internal Revenue Code, and contributions are tax deductible. Our next lecture, the annual President's Lecture, and the 386th meeting, will be the first meeting of 2018 and will take place on Friday, January 5th, 2018 at 8 p.m. right here in the Powell Auditorium of the Cosmos Club in Washington, D.C. The speaker will be Margaret Linen, Dean of the Scripps Institution of Oceanography and Vice Chancellor for Marine Sciences at the University of California, San Diego. She will be speaking on some very recent, interesting developments in oceanography and about some of the unique institutional facilities at the Scripps Institution of Oceanography that make these advances in oceanography possible. If you're a member, you will be receiving an invitation to the black tie dinner that precedes the lecture. The spring 2018 schedule is under construction. It's almost done. It's partially posted to the website. And as of now, the speakers will be Aviv Regev of MIT, the HHMI, and the Broad. And her topic is the catalog and diversity of cells. She's a great young researcher, and she's developed methods to do whole genome expression profiling, not new, but she does it on single cells. And she does it on single cells in a massively parallel fashion. And as a result, she's been able to gain a much greater understanding of the diversity of cells that we have in our bodies and of their dynamics and how they vary both within cell types and between cell types. On February 9th, Christopher Ralston of our own GWU here in town will be talking on cultural forgeries, basically antiquities fraud. He is a linguist and a brilliant one and is very blunt. So he's been in the news a bit, and you may want to read about some of the controversies that have surrounded some of what he has to say. But he will likely be telling us about the trade in antiquities and in forgeries, including how we detect them, and interestingly about the way in which antiquities forgeries affect people who may have religious beliefs tied to those forgeries, and those who are engaged in scholarship about them. On February 23rd, we have Thomas Zurbuchen of NASA. He'll be speaking on a topic to be determined. So actually, I know what the topic is, but I didn't have time to put it in the slide, so we'll keep it a secret. On March 23rd, we have Andrew Knoll of Harvard. He'll be talking on life on Earth, the deep history, which is basically on identifying and studying fossils that constitute the remains of the earliest living things that we know about, It's a subtle and a challenging art. As you can imagine, things from 1 billion years are not very well preserved in our fossil record, particularly since many of them, in fact, none of them had bones. So it bears on the question of how life originated on this planet, how it evolved and came into our present biosystem. What are the prospects for life on other planets? On April 6th, we have Jordi Puig-Svari of Cal Polytech, and he'll be talking on CubeSats. Should be able to speak with some authority since he is one of the inventors of CubeSats. And then on May 18th, we will have a number of speakers on Cassini. As many of you may know, Cassini had its last days this year, sadly plunged into Saturn, sending back useful data to the last moment of its long and productive life. And people will be studying the data from Cassini for decades, maybe for a century. And we hope to have some of the people who made Cassini possible and who ran Cassini while it was at Saturn, studying Saturn and its moons. And I'm sure there'll be lots of spectacular photographs, as well as a lot of interesting science. And so, I think with that, I will accept a motion from a member to adjourn the meeting to the social hour. Okay, Bob. And I have a second from a member. Eric, thank you. The meeting, how many in favor? And how many opposed? Nobody's opposed. So the meeting is now adjourned to the social hour, which ends at 10:30. And drive safely.